Let's try applying redox reactions with these equations. We're going to write the net ionic equation and show oxidation and reduction. So with number 1, we have zinc, HCl, hydrochloric acid. So this is a single replacement reaction, and in this reaction the chlorine will combine with the zinc, so these two will combine and then produce a gas. So the product of the reaction and chlorine, now zinc is a, chlorine is a 1 minus, that means we have to have ZnCl2 for the formula, and hydrogen gas. We need to balance the equation, so we need a 2 here. Now let's look at oxidation first. We're going to show oxidation and reduction. Now zinc in its elemental form, if we write its oxidation number, it's 0. Now chlorine is -1 and hydrogen is +1. Now on the product side, the hydrogen is now in the elemental form, so the hydrogen now is neutral, 0. The chlorine remains as -1, but the zinc now +2. Since we have 2 chlorine, that would -2, charge is 0. Oxidation numbers here, the zinc started off as neutral. It is +2. Went from neutral to +2, lost electrons. Oxidation is lost. So the zinc was oxidized. The same, it was -1 here and -1 there. So chlorine, nothing happened. Nothing changed in terms of electrons. But the hydrogen went from +1 to neutral, so hydrogen gained an electron, and so it was reduced. So the hydrogen gained electrons, or a reduction. Let's try another example. Or actually we need to finish the net ionic equation for this. So to write the net ionic equation, we'll need to break this into ions. We have zinc, solvent, and we'll write the complete ionic equation. We have 2H plus and 2 minus. Then zinc is an ion, it's aqueous, so that's dissociated. Zn, 2 plus, and we have chloride, Cl, 2 of those, aqueous, and then hydrogen gas, H2 gas. So we notice that the chloride is on both the it's and product side. That's a spectator ion, and but that's the only one. Interesting that the spectator ion is also the one that wasn't oxidized. It stayed the same. So the net ionic equation then is solid zinc plus 2 H plus ions makes Zn 2 plus and hydrogen gas. Let's try the second example. So in this example we have cadmium with nickel 2 nitrate, and the products here are the products of a single replacement reaction. So we would predict in this reaction, let's write it out. we would predict that the nitrate would bond with the cadmium. So in this reaction, the products then are the combination of nitrate and cadmium. So we have cadmium, which is a 2+ ion, CD, NO3, 2, and then nickel metal. So the oxidation that occurs in this reaction, the cadmium begins as neutral, the nickel is, in this case, positive 2. The nitrate as a whole, the sum of the nitrate is -1. The cadmium over here on this side, however, it now became an ion, so now it's positive 2. The nitrate remains as -1 as a whole. And the nickel is now neutral. So we see then that cadmium was oxidized. Cadmium lost electrons, and the nickel was it gained electrons to become neutral. The nitrate, neither happened. Typically when something's reduced also, it comes out of the form of a compound. So now we can write the net ionic equation. The nickel side here is 2+. Then we have nitrate ion, 2 of those. And then that cadmium ion and then so the spectator nitrate ions, so that the net ionic equation is CD cadmium plus nickel, aqueous nickel, makes cadmium ion and solid. Let's try the problem. We're going to use the activity series to predict whether metals would be oxidized. The activity series shows how readily a metal will oxidize in comparison to metals. And it determines whether a replacement reaction will occur. So the metal that's higher on the activity series forms a compound more readily, will oxidize more readily, more easily. So let's look at these examples here. We have the compound lead nitrate. So let's say we had the combination, the first combination here of zinc and lead nitrate. We want to know whether this would oxidize or not. So we look at the activity series and see which is higher. The comparison is between zinc and lead. So we have zinc right there and right there. So zinc is higher on the activity series. So zinc is higher than lead. What that means is that zinc is more likely to lose its electrons to nitrate, to donate its electrons to nitrate and form a bond with nitrate than lead. It has a stronger affinity for nitrate than lead. So the product of this reaction would be zinc nitrate and solid lead. So we notice that the nitrate switched from being with the lead to being with the zinc. So nitrate switched and went to go be with the zinc because zinc is higher on the activity series. So the answer, yes, this metal, the zinc, is oxidized. The zinc started off with an oxidation number of 0, and now it has an oxidation number of positive 2. So the zinc was in fact oxidized. Now if we looked at this next example, let's say we had the combination of copper and the lead nitrate. So we look at the activity series again. Now copper is right there, lead is right there, so we see that copper is lower than lead on the activity series. Well, that tells us that lead more readily oxidizes and donates its electrons to the nitrate than the copper. So the nitrate is going to stay bonded to the lead over the copper. So there's no reaction here, and copper is not oxidized. All right, next one. What if we had iron in combination with the lead nitrate? So iron is right here, and lead is right there. Iron's higher on the X series, so we would expect iron to have a stronger attraction for the electrons of nitrate, or stronger ability to donate electron nitrate. I just said that the wrong way. Iron is more likely to be oxidized, so we would have a reaction here. It would produce iron nitrate. So the combination of iron and nitrate, that could be Fe, probably Fe3+. So we'd have iron nitrate and then lead metal. Be balanced through there. Oops, that would actually be a 6 there, and a 2 right here, and a 6, and a 2. So we have going from being neutral to being positive 3. So we see oxidized, it lost its electron. So it's oxidized.